Hey Science Matters students, Mr. Clausen here. Just wanted to go over our Unit 3, Force and Newton's Laws, real quick with you. This is not meant to be a replacement for being in class and doing your work, but it is just a quick overview. So I will be talking pretty quickly in order to keep the video short. For this unit, we had four objectives, one for each one of Newton's laws, 1, 2, and 3, and then a fourth one for friction. And so we're going to be going through those here today. How we started out the unit, what we have here is an overlay of the classroom. And how we started the unit out is I asked you to try and push a bowling ball, get it to stop, get it to start moving again, moving around in a circle and throughout the classroom. And what a lot of us figured out is it was difficult to get the bowling ball started, and it was also difficult to stop the bowling ball or change its direction once it was already moving. And this is a good segue into Newton's first law of motion, which says that an object in motion will stay in motion, and an object at rest will stay at rest unless acted on by net force. Another way you can think about that is that basically, objects just want to keep doing whatever they were already doing. Well, if they're at rest, they want to stay at rest, and if they're in motion, they want to keep going in a straight line. And it's going to there's going to be some resistance to get them to change their ways. This resistance is what we call inertia. When inertia is an object's tendency to resist a change in its motion. And the more mass an object has, the more inertia it's going to have. All right, so we did some samples, or we talked about through some demos here on the side, and so we talked about little kids being pushed on a swing. If you had a little kid on a swing and you wanted to stop them from moving, they have less mass, so there's going to be less of resistance to change, and therefore they have less inertia, and you're able to bring a little kid to a stop pretty quickly. However, if I was on that swing and I asked you to stop me, because I have more mass, there's going to be more resistance because I have more inertia, and if I came swinging in, I'd probably pass my motion onto you and cause you to go flying. We also broke a brick on my hand. My hand was fine because the brick had a lot of mass and therefore did not move into my hand, causing pain. We also did a lot of demos where we had an object on top where it had mass, like the tablecloth or here with the bottles, and what we did is we pulled something out quickly, all right? And then because the object had mass to begin with, the object stayed at rest on top. All right. Now, we've been talking about the word mass, so it's important that we know what this word is. Mass is simply just the amount of matter in an object, and it's measured in kilograms. Now, not to be confused, and it's understandable why, but in everyday language, people sometimes use the word weight when they should be saying mass, and vice versa. Now, weight is the force of gravity pulling down on something, and it's measured in newtons. To calculate weight, what you do is you take an object's mass and you simply multiply it by the acceleration of gravity on Earth here, which is the number 9.8, and we figured that out. And so now what we have is a convenient way to take an object's mass and turn it into weight, or we can take an object's weight and turn it back into mass. Now, here's the thing that we wanted to remember. Remember I said if you're on planet Earth, there's a certain number of molecules inside your body, and gravity is going to pull you down a certain amount. However, if you flew to the moon, right, in a rocket ship or something, you're not going to lose any mass. Your mass is still going to stay the same, but you're going to weigh less on that planet, not because you lost atoms or molecules or anything like that, but because the moon is smaller and therefore the gravity is pulling you down on you more. All right, so that's Newton's first law. Objects keep doing whatever they're already doing. Let's take a look here with what a force is. A force is simply just a push or a pull, all right, and it's measured in newtons. And so I told you that if you want to think about how big a newton is, it's roughly the size of an apple, or if you were to hang up a quarter pounder, it's about the weight of a quarter pounder with cheese. A force is simply just a push or pull. So in order to get an object to change its motion, you're going to have to push it, which means to apply a force. And then often, though, objects will feel more than one force acting on them, and it can lead us to one of two scenarios. Either we have something where we call it balanced forces, where the two forces are the same, they basically cancel each other out. They're not necessarily the same size, but they're equal in size, or there's combination somehow that the forces all cancel each other out. Or what we have is where one side is bigger than the other, and that's what we call unbalanced forces. And so here we got a bigger force going to the left, a smaller force going to the right, and we have this little bit of force left over. Now this little bit of force left over is the result of the combination of all the forces being added together, and we call this the net force. Now often the symbols you'll see me use are this one here, sigma F, or force sub net. Remember this funny looking E is the Greek letter sigma, and in math it means to add together, and since the net force is the combination of all the forces, that's why we say sigma F. All right, now like I said, with balanced forces, there is no net force, and so there's no change in the object's motion. However, with unbalanced forces, the net force is not equal to zero, therefore there is a net force, and the object is going to accelerate or change its motion. The three ways an object can accelerate are speed up, slow down, or change direction. We took a few more examples of this when we learned how to draw a free body diagram. We learned there was many different forces. So for example, the force of gravity, the support force, which is the ground pushing up on an object, an applied force, which is just any force that's being applied to it, so it's usually the one that you're doing the pushing or the pulling, or there's friction, which is going backwards. And we looked at a couple examples here with the airplane. So in the first example, we had the airplane at rest, which means it's not accelerating, so there's no net force, meaning the forces must all cancel out. It doesn't mean that there's no forces on the object, it just means the net force is zero, because we still have gravity acting down, but the ground is pushing up at the same amount to balance that out, giving us a net force of equal to zero. However, at other times, like we have down here, and you'll notice that I'm no longer drawing the pretty airplane, drawing a box is totally fine. we do have a net force. So in this example, the airplane was supposed to be speeding up, which means it's going to be accelerating, and therefore it's going to have a net force. And that net force is going to be to the right. The way we can see it now is if we go back here and take a look. You have the applied force being a little bit bigger. You've got the friction force being a little bit smaller, and therefore, since the one to the right, the applied force is bigger, it's going there. I would encourage you to go back and look at your steps for how to draw force diagrams. Basically, you just draw a picture, identify the force acting on the object, label each one, and then identify if it's going to be balanced or unbalanced. And if we look back at this example, that's exactly what we did. Bringing us to Newton's second law. Now, we did a big, long lab. Essentially, the results were this, and not very shocking for some of us. Because there's a straight line here, if you increase the force, you're going to increase the acceleration, and this is called directly proportional. We found out that if you increase the mass, the acceleration goes down, and it actually came down in a curve like this, and in math we know that that is called a inversely proportional. Now if you put those two terms together, with the force being directly proportional to the acceleration and the mass being inversely proportional to the acceleration, you can combine those together here into this term, which is what Newton said. He said the force applied is directly proportional to its acceleration, and the mass is inversely proportional to its acceleration. You put those two together, you do a little algebra magic, and you see it the way you're more commonly used to seeing that, which is F equals ma. This also helps us define what a Newton is. A Newton is simply just 1 kilogram being multiplied or accelerated at 1 meter per second squared. Now you'll notice I've said some units there: force, mass, acceleration. You can see that force is in newtons, mass is in kilograms, and acceleration is meters per second. And that's because knowing those makes it very helpful when trying to solve problems like the one I have here. Whenever you try and solve a problem in physics or science, it's very helpful to list both your knowns and unknowns, which we have done. So this information was given to us in the problem, so we identified those here. And then it asked us for the acceleration, so we did this here. Next step is to identify the formula that you'd be working with that relates all three together. In this case, it was very simple. It's just Newton's second law, which is F equals ma. You go ahead and you plug the variables in. So the force in our case was 150 newtons, so we put that here. The mass was 10, we put that there, and then acceleration was what we're looking for, which is by itself. Using our algebra skills, since 10 is being multiplied by a, the only way to remove that from both sides is to divide it. And once you run that through, you're going to get your answer, which is 15. The math's not too hard. 150 divided by 10 is just 15. And then what we want to do is make sure that we include units. So acceleration is always measured in meters per second. Let's go to Newton's third law. Newton's third law, a lot of students can say, but when we found out that when it came to applying it, sometimes there was a bit of a disconnect. So for every action force, there's an equal and opposite reaction force. And it doesn't say sometimes, it says for every action force, there's always an equal and opposite reaction force. All right? And so what we'll often say here is that we say forces always happen in pairs. You can't have one force without another reaction force. These forces always act on different objects, and we did a lot of practice with that, dealing on our gold sheet there, finding the action-reaction pair. So for example, your fist hits the wall is going to hit your fist in return. How much? It's exactly the same size, just in opposite direction. Okay? You push on the wall pushes back on you. You pushing on the wall is the action force, the reaction force is the wall pushing back on you. Both are the same size. And if you step off a chair, the Earth's gravity is going to pull you down, which means your gravity is going to pull the Earth up. A lot of people want to say that the Earth is pulling you more, but that's not true. You're pulling each other the same, just like we have here with this bug hitting the windshield. When a bug hits the windshield hits the bug with the same force. A lot of the time we want to think that one of those forces is bigger than the other, but it's not. And I think this example from one of your homework assignments does a really good job of explaining it. Hopefully you picked disagree, and the reason what we have going on here is a father and a daughter are rollerblading, and they push each other away. Now the father ends up accelerating much slower than the daughter. So you might want to say something like, well, since she accelerated more, therefore there's more force. And if we go back to what Newton's third law tells us, it says that each action and reaction force is equal in size but opposite in direction. So how does this work? The force is the same. That's what Newton's third law says. But Newton's second law is also at play here. So because the daughter has less mass, she's going to accelerate more. So take a look over here. Try to do it with some equations to help us out. Both of them are going to feel the same size force. But because the daughter has such a small mass, her acceleration is going to be very large. The father on the other side, feeling that same force, is going to have a very small acceleration because he is much, much, much larger with his mass. Same thing holds true with the bug in the car or you in the earth. In both of those cases, one of the objects is bigger than the other, and therefore, even though they're feeling the same force, their accelerations are vastly different. This brings us to our final objective, which is to know a little bit about how friction works. And for a lot of it, it's just the fact that friction is a force that opposes motion. Now, where does this force come from? Well, whenever you have two objects moving together, friction is always going to go opposite of the direction you want to go. So this person's trying to pull it to the right, friction's pulling it back this way. Where's that friction coming from? Well, it's coming from how the two surfaces interact. If you were to zoom in on where the box is being dragged against the ground, you're going to see these tiny little bumps that are going to get in the way. This is going to prevent the two surfaces from sliding easily, and this is a main cause of what friction is. From this, we were then able to figure out in lab, we did some more experiments, and we wanted to figure out, or we found out the different types of friction. The first two being, the main categories are static and kinetic. Static means not moving, and kinetic means moving. And the way we knew that there were two of them is when we looked at the graph spiked, and then it plateaued out. And the spike, was when the block wasn't moving yet. And so it took a lot of force to get the box moving, and we call that static friction. Static means not moving. Once the box got moving, then the friction dropped down drastically, so it went way further down there. And we call this kinetic. Now in our case, it was specifically what we call sliding friction because the two surfaces are sliding together. But there's also what we call rolling, and that's what a wheel would feel or a ball rolling on the ground. It's a little bit different. And then there's also fluid friction, which an example of would be air resistance or something moving through the water, because both water and air are both considered to be fluids. Now if you rank these, static is always going to be the strongest, followed by sliding, then rolling, and then fluid being the weakest. We talked about how we could change the amount of friction on an object. There's essentially two ways to do it. One is make the thing heavier or push the two surfaces together. And this makes a lot of sense because if we were to take these two surfaces and push them together, those teeth are going to interact more and it's going to increase the friction. The other way, which is the more common way that people think about changing friction, is to change the surface type. And in general, the rougher the surface means there's going to be more friction. Now, there are some exceptions to this. And so what scientists did is they came up with a way to measure it. And the way that they measure the type of surfaces that are in contact and how much friction they're going to be is through this term of what we call the coefficient of friction. Now, I can't stress this enough. The coefficient of friction simply measures the type of surfaces that are in contact with each other. So it's a way of ranking how much friction is going to be between two surfaces when the friction is there. The way you calculate it is you take the force of friction divided by the normal force. But what we use is this Greek letter mu. It looks like an M and a U combined together to show or to tell us how much friction two surfaces are going to have. The way I helped you remember it is I tried to take the Greek letter mu and turn it into the picture of a cat and then say mu because that's what kitties say. The big takeaway from this is the smaller the mu, the less friction. So the smaller the coefficient of friction, the less friction there's going to be. The larger the coefficient of friction, the more friction there's going to be between those two surfaces. An example of this is perhaps this happened when you were growing up. I know I used to do it. Why do I say used to? I still do this. Whenever there's a nice wood floor and I'm wearing socks, and especially after it's just been cleaned, I like to run out on the wood floor and then slide very easily. And this is because the coefficient of friction between the wood floor and my socks is very small. It's something like, say, 0.3. However, I often find that when I get to the end of the hallway and I hit the living room or wherever they start to have carpet, my socks no longer keep sliding very easily. They stop very quickly, and this is because the coefficient of friction, or the mu value, increases between socks and carpet. So socks and carpet, a lot of friction. Socks and wood floor, very little friction. So that's how the coefficient of friction works. Like I said, this is just meant to be a quick review. It's not going to cover everything else. Hopefully this works out well for you. Work on the review packet that you have in your the last few pages in your note packet. There is a review, and it does look something like this. I did share the answer key. Here it is, the one I was looking for. I did share this answer key with you, so you would be able to check your work on some of these sample problems. Hope everything goes well, and I'll see you when I see you.